Hello, welcome to CosKASI ECR seminar. Today we have our own Miguel Icaza. Miguel did his master's in UNAM in Mexico and did a PhD in Durham University. And today he's going to present his work that we'll find out soon. So please go ahead when you're ready.
Yeah, thank you. So I think most of you already know me. Thank you for the introduction. I'm Miguel. I've been here in CosKASI for a bit over a year now, working with Johnson Song and a subset of his current and previous students, including Christoph. And so during my time here, I've been focusing on mainly 4 projects. I've been dipping my toes in a couple of extra projects, but this has been like the main focus of my research. I can obviously not summarize 4 projects in an hour, so I decided to focus mostly on one of the projects, but I also wanted to give a quick introduction to another one, which is the one that I'm currently focusing on. So out of these 4 projects, one of them was a continuation from my PhD, where I'm using sparse regression methods to study the galaxy halo connection, but I think almost everyone here has heard me talk about that one at some point, so I'm not gonna mention it here. I've also worked on a project that we're starting to write up at the moment with collaborators in Mexico, where we use neural networks to emulate some models that are the Gaussian streaming models for the correlation function. But in a month, we will have one of my collaborators in this seminar. So in order to overlap, I will also not talk about that project. And then out of the 2 remaining projects, one of them is I'm trying to build mocks for the luminous red galaxy survey of DESI using machine learning methods. I will probably gloss over that project a little bit because it's not that completed yet. And then the main focus of this talk will be a project in which I am using Gaussian emulators, which are machine learning techniques to try to estimate these theoretical templates of the power spectrum that we build with these models called different models. But anyways, before I start, I wanted to very briefly give a summary of how the analysis of a large-scale structure survey to find the best fit values of cosmological parameters looks like. So when you hear that someone is working in a large-scale structure survey like DESI or EVOS or something like that, they are probably working in a subset of this diagram over here. Basically, to make the analysis, you need 3 components. The first one is data, probably from the simulation itself or something like that, or simulations, normally embodied simulations. And this is so that you can test that your methodology is working correctly. So because you build the simulation with a known cosmology, if your methodology is capable of recovering the parameters, then it means that your methodology probably works. The second ingredient that we normally have is a model. The model should depend obviously on a set of parameters. And then when you change these parameters, the model should change. And what you're trying to find is the value of these parameters that better fit your data. And then finally, some error estimates. I am not an expert of this, but I think the most common approach is to use quick mocks, which is basically methodologies that approximate the power spectrum, and they are methodologies that are efficient enough to be able to run it thousands of times with different initial conditions. This is, for example, what the easy mocks DESI do. And if you have these 3 components, you can combine them on an estimate on an estimate of the goodness of it, for example, the chi-square or a posterior distribution or something like that, and then you can later explore with, for example, an MCMC. So yeah, when you work on a large-scale structure survey, you're probably doing something related to one of these points in the plot. Okay, so now I'm gonna be a bit more specific, talk about one of the projects that I'm working on. And so just to introduce the project, as I just mentioned, one of the things that you can do is use simulations, test your data. But because large-scale structure surveys have such a large volume, you would need to run dark matter only simulations. Astronomical simulations are too expensive to be run at that volume with the right resolution. And so you also need to come out with a way of painting galaxies into those halos. And as we heard last ECR seminar, the one of the most common approaches to do this. It's a function known as halo occupational distributions. And it basically, I'm not going to go into details, but the very basic idea is that you grab a halo property that is most of the times the halo mass, and then you compute for a given halo mass what is the probability that that halo has a galaxy of your survey, and then you also compute how many satellites should that halo have. What we're trying to do in this project is come out with an independent approach, so like a way of having something that is not the HOD to be able to do this. We want to do this, well, first of all, because having a secondary test to corroborate HOD results is always good. But more in particular, when because we're going to use a machine learning algorithm that uses more properties that are not only the halo mass, we might be able to get a bit of a more of a realistic connection. And so when you look at the smaller scales, the halo mass is good to know which galaxies to paint. But when you have small scales, there's other factors that come in, which that's normally called the assembly bias. And if you're only using the halo mass, then the connection is not that good, and the HODs are a bit not amazing at the smaller scales. So hopefully this is a different methodology to do this. The very basic idea is that we go to a simulation, a aerodynamical simulation in a small volume where you can run with enough resolution. Right now we're using Eagle. We're probably gonna switch to Illustrious or something like that because we probably need more volume. And then in Eagle, because it's an aerodynamical simulation, you have baryons and you can measure stuff like stellar masses and colors. And if you have the stellar mass and the color of a galaxy, you can guess if it's an LRG or not. And so you can make an Eagle LRG sample. I'm going to go into details about how we do that because I don't have time. And then we look at these galaxies. We look at which ones are an LRG or not. And we also look at the halo properties. We feed all of this to a machine learning algorithm, and we hope that it's able to learn a relation. And then our idea is to grab a larger simulation like the MDPL2 simulation and use these relations to map galaxies into the larger simulation. Well, random forest, this is basically because of the size of Eagle. Eagle has like tens of thousands of halos that are large enough to maybe contain an LRG. And so random forest works canonically well at these sample sizes. Or something like a neural network or such canonically is considered to require probably a bit more data. I've tried both. They both seem to work relatively okay, but yeah, I'm sticking with random forest for now. And then more specifically, because this is an imbalanced classification problem, so approximately only 1% of the galaxies in Eagle might be an LRG. Of the halos in Eagle, sorry, might contain an LRG. And so you need an algorithm that is good with like these samples in which almost nothing is what you're looking for and only a very small subset is. And just have in mind that if you try to naively run any machine learning algorithm, the algorithm will be the algorithm will never want to predict something as an LRG, because if it never selects an LRG, it has 99% accuracy. So you need to come up with ways of working with this. And there's a bunch of methodologies in random forest that work with that. We're using the one that is in that paper in case of this interest. Here are some preliminary results. It's not, we don't have the accuracy that we want yet, but so what this plot is showing is you have in the x-axis, you have the stellar mass of galaxies in Eagle, and in the y-axis, you have the color of galaxies in Eagle. And then each dot represents a point in our test set. So these are data that was not used for training the model. And that little black box correspond galaxies that we consider that are massive enough and red enough to be considered LRGs. So everything inside that box should be an LRG. And then the colors represent what was actually predicted as LRG in red and what was not predicted as an LRG in green. So two things are like apparent from this plot. The first one is that our algorithm is good at selecting LRGs as LRGs. Almost everything inside of the black box is red. So all the LRGs, almost all the LRGs were considered LRGs. And the ones that are not are very close to the border, so maybe it's a bit ambiguous if they were or not. But then another thing that is very apparent is that we have a large sample of blue massive galaxies that are contaminating our sample. So this region in the bottom here, this region in the bottom right here, we have a lot of galaxies that are considered as LRG but aren't. So a conclusion that I get from looking at this is that we are not very good at predicting color yet. We're better at predicting stellar mass, which is something to be expected. In general, we know that modeling color is very, very hard. These are some results from people that have tried to do it in very large data sets using very precise embody simulations, and these are very good works. And you can see how, so the black line is the one-to-one line, the vertical axis of both plots is the predicted value, and the x-axis is the true value. You can see that when you have a red galaxy, there is a big dispersion of, so when you predict something as red, there's a big dispersion of galaxies that were actually included in the true value. So this is something hard to do. So the short answer is we're not very good at predicting color because predicting color is hard. But the longer answer is that I believe that most of these studies use halo properties that are well correlated with stellar mass, like halo mass, and therefore are very good at predicting stellar mass, but they don't include properties that parameterize assembly bias that well, because it's difficult to parameterize assembly bias that well. And so what we're trying to do at the moment is including other parameterizations that maybe are better at modeling assembly bias. For example, the number of subhalos and the number of mergers that a halo had in its history. And so we are parameterizing that, including in our data set, and we're also switching to a larger data set, and maybe this will improve our modeling a little bit. But in any case, even now that we have this contamination of blue massive galaxies in our sample, when we look at the halo mass functions that we get, and we compare them to the ones that you get with HOD models, we see that the shape is similar, pretty similar, even if the amplitude is a bit different because we are over predicting certain galaxies. And we also note that we get some other properties correctly. For example, the ratio of satellites and central LRGs is right. And yeah, the conclusion is for this project, our conclusion is we still have some work to do. We need to improve our modeling, but our results so far seem to be consistent with HOD. And what we hope is that once we can actually model this properly, we can come up with our own HOD parameterization. That is, that is something to be seen. All right, so for the rest of this talk, I want to switch to another project. Sorry for the switching of topics. And now I want to talk about a project that we are running up now. I was hoping to have final results right now, but as many of you guys might know, our computer cluster here at CosKASI has been a bit unstable recently. Some nodes have been broken, and some connection of outsiders using VPN is not working very well. So unfortunately, I don't have the simulations yet, but yeah, so I cannot show the final results, but yeah, I'll present the rest of the work. All right, going a little bit back to the beginning of this talk, as I mentioned, when one is in a large-scale structure survey, trying to predict the value of cosmological parameters, what you have to do is you have to come out with a model that depends on free parameters and then feed those free parameters to data. This is an example of some work that we did with EBOS a couple of years ago. One of the issues with this is that in order to get these constraints, one needs to explore the parameter space using most of the times a Monte Carlo Markov chain. But then, as I'm sure a lot of you know, when the parameter space that you're exploring becomes large, the number of evaluations that you need in your Monte Carlo chain can be very, very large. This is particularly important in the new models that are coming out that probably have 10 or 11 free parameters or something like that. And then they require probably tens of millions of evaluation, even hundreds of millions of evaluation. And then if you need that many evaluations, then obviously you need an efficient way of coming out with each of these models. But then there is a trade-back because the best models that you have are probably not the most efficient ones. They're probably the opposite. They're probably the most expensive ones. And so there is motivation to come up with ways of learning how to evaluate these models better. And recently, machine learning techniques have been used for this. And so the idea is that you run your model in a bunch of training points, and you feed that to the machine learning model. Hopefully, the machine learning model learns how to predict it. And certain machine learning models have almost immediate evaluation times. So yeah, the problem of evaluating gets disappears from the MCMC, from the problem of running the SMC. So that is what we're going to do now. We're working on building an emulator for a set of theoretical templates that my supervisor designed a couple of years ago before I came here. These models are called hybrid models, and I'll explain why in a second. But the idea behind the project is this one. Behind the models is this one. So we have done second-order perturbation theory for a while, almost 10 years now, and we can do it pretty well. There are some public codes that do second-order perturbation theory power spectrums very well. But in the new surveys with the new volumes, we are starting to need higher order corrections that go below second order. And so the suggestion of the work of these hybrid models is that, okay, suppose that we could compute the higher order corrections in a fiducial cosmology. And they propose a set of scale relations that allows you to transform those higher order corrections from one cosmology to the other. And this is only true for certain cosmological parameters, specifically those cosmological parameters that only affect the amplitude and the scale of the power spectrum. For example, little h or 8s. And so what this allows you to do is that because canonically, to compute the matter power spectrum, you need 5 or 6 cosmological parameters. If you find these scaling relationships, now you only need 3, right? So it reduces the number of free parameters that you need significantly. Okay, so how do you find these higher order corrections in a given fiducial cosmology? Well, if you were to run a very precise embodied simulation, then you can probably approximate the higher order corrections as the difference between the second order perturbation theory predictions and the embodied simulation. Okay, so this is what they do. And they come out with this methodology that can actually get sub-% error accuracy even at pretty small scales. Okay, this is a bit of a schematic of what we're doing. We have so we need an embodied simulation in the fiducial cosmology, a second order perturbation theory template in the fiducial cosmology. We feed that to our hybrid model, and it generates a power spectrum. Okay, and so I put a bunch of free parameters in the bottom. Those of you that know a little bit about this might notice that the hybrid model also does a correction from going from the matter power spectrum to the galaxy power spectrum with 2 degrees of freedom, which are those bias parameters. It also transformed to the redshift space with like those growth functions and such, and it also allows for the Alcock-Paczynski effect. And so, so this hybrid model goes from the matter power spectrum in real space with 2 fixed parameters to the whole galaxy power spectrum. And so there's 3 steps that need to be done. The first one is to run an embodied simulation that's pretty slow. Even if our cluster was working at full capacity, we will need like half a day to generate one. So we can maybe generate, I don't know, 30 before everyone gets super mad at us because the cluster is always busy. And then we also, okay, so we cannot generate a lot of embodied simulations. That's like our bottleneck. Also, the second order perturbation theory predictions, we can generate maybe like 1 a minute. So we can definitely generate tens of thousands, hundreds of thousands, but probably not hundreds of millions or whatever you will need to do a MCMC chain. And then the final part, which is just the hybrid model code, that one is already very, very optimized. It requires a fraction of a second, so we don't need to worry about that. And so what we will do in this work is try to optimize the generation of embodies and second order perturbation theory predictions. Okay, and so the way that we're going to do this is by using this methodology known as Gaussian process. For those of you that listened to Rodrigo talk yesterday, he already sort of introduced them already, so I'm gonna repeat some of that stuff. But something important to notice is that Gaussian process is an interpolator methodology. So what that means is that if you are trying to guess a new point, your methodology will work the best if it is close to a point that you've already noticed before. And so what this means is that when you are training your model, the more points you get, the better. And if you sample your whole space thoroughly, then your model will be better. But we have an issue because we need to sample our whole space thoroughly, but with as little points as possible, because each point means a new n-body simulation, which is expensive. And so in order to come out with these spaces that sample everything thoroughly, but with as little points as possible, we use an algorithm that is known as the Einling algorithm. I don't know how to pronounce it, but yeah, that's how it's written. I'm just going to gloss over what you do. And if you want more details, you can look at them in that paper. And so the very basic idea is that you begin with a symmetric Latin hypercube. For those of you that don't remember what a symmetric Latin hypercube is. Okay, so a Latin hypercube is basically you have your parameter space. Here's an example in 2 dimensions. And then let's say that you want to make a symmetric Latin hypercube of 30 points. You divide your space in 30 rows and 30 columns, and then you put points in such a way that each row and each column only has 1 point. That's a Latin hypercube. And a symmetric Latin hypercube just means that the reflection of each point in your grid through the center is also a point in your grid, which is what is shown there by those black lines. And we also include the center as one of our training points. Okay, and then what the algorithm does is it chooses a dimension and then it swaps 2 random points in that dimension. That's shown there. The pink points used to be points in the algorithm, and it randomly switched the position of those 2 in the vertical dimension, and now you have 2 new points. And because you want to keep the algorithm symmetric, you also switch the reflection to the new points that you will need to keep the algorithm symmetric. Okay. Okay, so that's good. And every time you do a flip, you might get a better distribution or a worse distribution. So the next thing that you need is a metric that allows you to check that. We are using the average distance of all points. And so if the average distance is larger, we believe that that distribution is better suited for our purposes. Okay, so you do this, and every time that you switch to a permutation that gives you a better grid, you keep that, and every time that you switch to a permutation that gives you a worse grid, you might move there or not with a probability. So it's a bit like the idea behind an MCMC chain. And so you do this to explore the space of all possible permutations, and in the end, you keep the one that is the maximum of your metric. Yeah, so and because it's weakly dependent on the initial grid that you give it, we generate 40 random Latin hypercube grids and run these 40 times. And in the end, we just choose out of all of the grids that we explore, the one that is the better. And this is an example of what you get after running the algorithm for a bit. So here's a grid, and again, it's good. The space is thoroughly sampled, but it could be improved. And this is how it looks after running the algorithm. Okay. Right. So we generate our grids. And now for each of those grids, we need to run an n-body simulation. We end up with, so let's say that we have a grid of 30 points. We now have 30 n-body simulations. For each of those n-body simulations, we can compute a power spectrum, and then we have a matrix of 30 power spectrums that we want to use to train our emulator. If we were to try to predict the power spectrum in a new point directly, we will need to predict 1 value for each value of k that we use. As you guys may know, power spectrums sometimes have like hundreds of values of k or more. So this is not very efficient because we'll need to do hundreds of predictions for 1 power spectrum. A better way to do this is to use singular value decomposition to write the power spectrum as a set of eigenmatrix, eigenvalues, and eigenvectors. And so the basic idea is that you write the power spectrum. So as it's shown down there, you have eigenvectors that have the dependence of k, and then the dependence in the cosmology only comes in the weights. And every new power spectrum is a linear combination of that. And if you order the eigenvectors by importance, then the first eigenvectors are the ones that do most of the modeling, and after a while, it's just very minor corrections. as I will show in a bit, if we keep only the first 4 or 5 eigenvectors, we are already way below 1% accuracy. So you reduce the problem of trying to guess 100 points to try to guess 4 or 5 points. And now what you still need to do is to model your weights. So we have 4 or 5 weights to model, and each of them will be modeled with a Gaussian process. I don't want to go into a lot of details of Gaussian process because the math can get tricky, but the basic idea is this. You have some data that looks like points in parameter space and weights. You can normalize the weights in whatever way you find it appropriate. And now what you're trying to find is the weight for a new weight for a new point in parameter space. You can suppose that you have a kernel, and I will give the value of the kernel in a second. This is basically just a function, because we're doing an interpolation, that tells you for 2 points at a given distance, how similar or different they should be to each other. And this kernel depends on a set of hyperparameters that you need to fit. Okay, anyway, suppose that you have a kernel and that you know the value of the hyperparameters, then the assumption of Gaussian processes is that the distribution for the weights in your training set and the weights in your test set, it's a multivariate normal distribution centered around 0 and with a covariance matrix given by the kernels of, so the kernels as they are represented there, with the top left corner being the kernels of points in the training set with points in the training set, and then the bottom right corner, test set, and then the covariance. Okay, and so once you have that, and you do all of the maths of Gaussian process, you get to the conclusion that for a new weight, you can represent it also as a normal distribution, and that is the equation for the mean of that normal distribution, and that is the equation for the standard deviation that works as an estimate of your uncertainty on the prediction. I will come back to that in a second. But yeah, for now, the next thing that I need to do is to show a kernel, because from the equation previously, if I have a value of the kernel, I can finish the prediction. So the way that I found the kernel and its hyperparameters, the details are in that paper that I have in the top right corner. But that is the basic shape. So you have a set of 3 parameters. There are like 30 of them. These raw parameters tells you for each principal component, sorry, eigenvector, and for each dimension in parameter space, how close 2 points need to be together to be similar, or for that the interpolation doesn't matter anymore. You also have some estimate of the error of the methodology for one particular Gaussian process, but then you also need to combine all of the errors to have the error of the whole process that includes imperfections, let's say in the embody simulation, truncation errors, etc., and then adds a final 3 parameters. So in general, you have like 33 parameters that you need to fit simultaneously, because they are all combined with each other. And what you do is you do a bunch of assumptions from the priors of these parameters, and then just compute the posterior probability. The expression for the posterior is complicated. It's like 5 pages of equations, but if you go to that paper, you see the answer and you code it. And yeah, so every time that someone says that they are training a Gaussian process, what they mean is they are trying to find the best fit value of that posterior probability for the parameters. Okay, so one point that I want to emphasize is that, as I just mentioned, you have the Gaussian process gives you a new point estimates of the mean, which you can consider it as your prediction, but also of the uncertainty that the methodology has about that prediction. To illustrate this, I took this very basic picture from the scikit tutorial. This is, yeah, just like a Python tool, and they have a tutorial on Gaussian process. And so the red points represent like training points, and then the blue line is the best fit model that they get using the Gaussian process. And then these like volumes are like the 2 sigma estimates of their estimates of the uncertainty. So what's important for us is that imagine that we now want to make this model better, that we don't have the accuracy that we want. We can go and look at where is the uncertainty the largest. And if we were to use that point, run an embody simulation in that point, then we will reduce the error where the error is the largest. So this helps us know which regions in parameter space we want to explore better if we want to improve our model. And this will be important in a second. Okay, I'm almost done. I'm just going to show some results. I was hoping to show models on the embodied simulations themselves, but unfortunately, we're still running them. So these are just results on a second-order perturbation theory polynomial. Probably I saw that. And so, yeah, so the black line is it's not CAM. It's a second-order perturbation theory thing. Sorry about the wrong label. But yeah, so the black line is the original power spectrum, and then we try to emulate it with a model that we built. And each line represents more and more eigenvectors. And as you guys can see, when we include 5 eigenvectors, the error is way below 1%, right? Now, so actually, since the second or third eigenvector, the error is already below 1%. Okay, and so the way that we are working with this right now is we start with a grid of 12 simulations. We know that 12 simulations is probably not going to be good enough because it's barely good enough to work with second-order perturbation theory, which is simpler than embodied simulations. And so we're going to finish our 12 simulations. We're going to build a Gaussian process and use it to predict the next points that we want to explore in our embodied simulations. And we're going to keep doing this until the last 2 points that we build have a below % accuracy. So in this way, we start with a given grid that we know is not going to be good enough, and then we keep adding points until our grid has the accuracy that we want. And this way, we minimize the number of embodied simulations that we want to run. This is a bit similar to what we heard in the last ECR seminar, right? Okay, and finally, these are the results for the second-order perturbation theory model. In here, we don't really need to worry about running as little points as possible. Each of these runs requires like a model, like a minute. And so we can generate hundreds of them. So for each simulation at each redshift, I run 200 simulations, 100 for test and 100 for training, because I'm worrying about 3 redshifts, which are the redshifts of the 3 main surveys of DESI. I generate 600 second-order perturbation theory models. And what I'm showing here is the percentual errors on the test set. So I build a Gaussian process emulator using 100 points, and I use that emulator to test the 100 points in the test set. And then what these plots show, we have one plot, one line per. So we have 9 lines in the same for the same color. We have 3 lines, which are 3 different redshifts, and then the different colors represent the percentile of errors that we have. So the percent error. So the blue line corresponds to the line below which half of our errors lay, and then the red line is 68, and the green line is 95. So this was a bit shocking for us when we saw this, because as you guys can see, we're predicting the results not only below 1% error, but below 0.001% error, which is crazy accuracy, except for like these peaks, but these are just the model being a bit unstable in those regions. And so we tried to understand why were we able to generate models that accurately. And we concluded that it's because of 2 reasons. The first one is because hybrid models allows us to only model 3 dimensions, so three parameters, omega B, omega C, and NS. If we were to move to 5 dimensions, we will have worse models. And the other one is because we are using Planck 2018 constraints and 5 sigma, but Planck 2018 is already crazy small. So we are able to do models this accurate because we only need 3 dimensions with constraints that are already pretty good. If I were to run with like the constraints that we'll have like 10 years ago in more free parameters, I did this as an example, and as you can see, the errors are very close to 1% errors. Okay, so that is all for me. Here are some takeaway points, and I am very happy to listen to your questions if you have any.
We've got some time for questions. Yeah, any questions? While people think about it, can we go to the slide where you talk about the kernels used for GP? I was wondering if, yeah. So this, I was wondering how the kernel was chosen. Are there some free parameters that goes into the kernel itself?
Yeah, this is a free parameter and this is a free parameter. Well, these are a lot of free parameters, and this is one free parameter per a vector.
Right.
And so you have total, I have like 23 parameters or so.
Yeah.
And then if you go to this paper, they'll have a value for this, which is the posterior probability for your free parameters as a function of your data.
Yeah.
And so you can explore these. You can explore this parameter space with MCNC or whatever you want, and yeah, find the best fit values to your data.
So the choice of these hyperparameters depend on which data.
The input power, the training data, the training data gives you a power spectrum that you can divide into 5 weights, one per component. Those weights.
Right. Okay. But then they are tested on like different data.
Yeah. So yeah, you train it here, you build. So once you find these values, your Gaussian emulator is built, and then you use it to predict test data.
Christian?
So it seems that you are exploring very small cosmological particle space, right? Which is given by the Planck 2080, right?
Yeah. So
yeah. So did you try this? I mean, putting a polynomial and seeing if that works, because Gaussian process seems too complicated, right? If it's very small thing, I expect that you can write a Taylor expansion around all the points, and they would also give you, to a certain degree, it will give you the results, right?
And the results are not
because you want to see the impact of this, what happens if I change the small value of omega m thing, right? So for each k bin, I can write a Taylor series expansion. So each point moves either little up or little down, right? Adding omega m little bit does not introduce 3 more wiggles into the power spectrum, right?
Yeah.
So why so much complication? I mean, did you guys try this?
No. We've only tested with Gaussian processes so far. Yeah, I mean, it might be good to try to test a simple model.
Okay. There's a little bit of historical thing in this as well, right? Emulators go back to like, I think the first power spectrum emulator goes back to like 2016, 2015, I think the first.
Yeah, I mean, for everybody simulations is 2010, the one.
Yeah, really?
Yeah.
Okay.
27, 28, something like that.
Yeah. Using GP.
Yeah.
Really? 2007 for GP?
No, 2010, I think it was.
2010 is Hartman, but like, if you look at the papers where he developed some of the theory, they're a couple of years older.
I told that Armin was the first person to use GP cosmology.
Actually, with not Catherine Heidman, but her husband. Anyway, so they were the first ones who used GP in cosmology.
Yeah,
I think before Armin, and that was, I think that was the 2010.
So can you explain actually how this algorithm works? Like how do you find the parameters where you want to select for the simulation, in simulation?
the test set, you mean?
Like if I understand correctly, you are choosing the parameters, like points in a parameter space.
Yeah. This one.
Yeah.
You mean how to choose points and
Yeah.
parameters? Yeah. Sure. Just before I switch to that, one last thing that I wanted to mention is that we might get away with using simple models. I don't know how to test. In our project that we're studying right now, though, we're going to try to do this for HOD fittings, and in there we definitely will have more parameters. So in any case, this methodology. Yeah. Anyway, so back to your question. Sorry. So So you start with a random symmetric Latin hypercube. Did you more or less understood what that was when I explained it? If not, I can repeat it, don't worry. So basically, if you have let's say that you want to find points in a two-dimensional grid for this example, we are actually using more dimensions. Basically, what you do is you divide your space into columns and rows, and then you put points in such a way that no column has more than 2 points, a bit like Sudoku if you want.
Okay.
And that's a Latin hypercube, and then you just make it symmetric, which is what's shown here, that like every point, their reflection through the center is also part of your grid. So that's how you start, and then you do this algorithm that I was mentioning, in which you randomly switch, you choose a dimension, switch to points like these ones, you move them like from here to here, and then you also move the points so that it stays symmetric. And then, so that is one permutation. It might get better or worse after you do the permutation. And you basically use the algorithm that I showed there to search the parameter space of possible permutations for the best one.
So, like, you already have a number of parameters, that number of points that you want to finally choose, or that depends on how much accuracy you need. How do you select the final number?
Right. So choosing the number of points is also part of what we're interested in doing. As I mentioned, we don't want a lot of points. We want as little as possible. We're probably gonna require like 16, 17, I don't know, embodied simulations to get accuracy below 1%. And so we start with something that we know is not gonna be good enough. Let's say 10. That's what we're doing right now. So we get those 10. We build a Gaussian process. The accuracy is probably not good enough, but then we use that Gaussian process to know where the next point should be. And then that's how we choose the 11, the 12, 13, and so on, until we get the 1% accuracy. And that's when we stop.
So this is basically, so in our field, like we basically maybe say the same thing, but it's called a greedy algorithm, the greedy search. So you basically, so what we do in gravitational wave is that if we want to do some numerical simulation, we build this so-called surrogate model, which are trained on actual numerical simulation of the black hole binary system. But we want to figure out like what is the points in our parameter space that are best to build this model. And I think it is similar that we start at some corner points and we select the next one by building a model from the existing points and then compare the error and choose the maximum error point. So
that's it. Yeah, that's what we do with Gaussian process. We just don't start with corner points. We start with this distribution of points.
Okay, so this you start from this distribution of points.
Yeah.
Okay. So usually, like, what did you find? Like, what is the number of points you needed to make a?
So for the models that I just shown that have crazy good accuracy, probably like 20 or 30 are enough. I'm using 100 because I can. They're not expensive. For embodied simulations, I don't know yet. So we're running them already. I don't know, 20, hopefully. I don't know. We'll see. Yeah.
And how does this scale with, like, if you add more parameters, like dimensionality of your model?
You mean how does
like if your model has like 3 parameters, right?
Yeah.
So if your model like
have 5 parameters,
yes.
How much more points will we need?
Yeah.
So I don't know the exact answer to that. I can tell you that it's not exponential. I think for the test that I've done, it looks arithmetic. So every new dimension, probably 20 more, 10 more points or something. But I don't know the real answer. Yeah.
But can I ask a quick follow-up? You're using this to select the points and then run the n-body sim, right?
Yeah.
So this is a way of just fixing all of the different simulations you're going to run, effectively, the cosmological parameters associated with the different simulations.
Yes.
So you don't, once this is selected, once you finish running this annealing algorithm, there's no opportunity to go back except to running new test cases.
Yeah, so that's why we know that the algorithm is good at selecting a sparse space. But as you just pointed out, so if you had a sparse space with 12, with 10 points, and then you build a simulation there, maybe the next point that it will choose, it wouldn't be the same one that if you started with a sparse space of 11 points, right? So that's why, that's one of the main reasons why we start small and we start only with 10 points, so that the next point that we choose, it's always in the region where the algorithm is more uncertain about its error.
So it's like the worst, but not like the worst possible case, but
Yes, yeah.
yeah.
So it's definitely the worst, well, I mean, I don't know, because it's a three-dimensional,
Yeah.
right? But it is a place where the algorithm is very uncertain about it. And so another good thing about that is that, let's say that we have 15 grid points and we can build an emulator that predicts 16 and 17 with below sub% accuracy. We're predicting 2 of the worst points that we could with sub% accuracy.
So how sensitive is your method on the initial points, the initial distribution?
It's very sensitive. If I screw up and put 2 points that are super close to each other, they basically give me nothing new. So like if I run 10 points or 16 points, but the 16 points are not that well sparse, it's definitely going to be much worse than the 10 points.
I'm asking this because actually this kind of sparse distribution, we had noticed that it's not the best distribution. As I said, like if we start but that may be the case specific result, but if you start from the corner points, in our case, it actually needs less point than.
But are you doing an interpolation though? Like is your method an interpolator?
It could be, it's the interpolator actually.
Right. Because that's the thing about the Gaussian process, right? There are local interpolators, so they really depend on having a point that is closer than whatever free parameter you got here, right? So this tells you how close the points need to be, and if you don't have 2 points that are closer than that, maybe in that dimension you're not going to do the right thing.
Can I ask? Probably this is very naive, but why is the need of this hybrid modeling between a loop perturbation theory with on top and body? So it's just to gain in computational power or accuracy, or I mean, what does two-loop perturbation theory add on top of n-body? Because if with your emulator of n-body you get a 1% accuracy, how does the...
So that's not a naive question. I think that's a very important question for this topic. The reason why we get that good accuracy, and again, I'm getting this good accuracy on a second order perturbation theory model. It doesn't mean that I'm going to get it in n-body simulations. But the reason why we get that good agreement is because we are only using 3 dimensions, not 2. And the reason why we're only using 3 dimensions is because of the of our hybrid model allowing us to fix 2 of the scale and amplitude dimensions, right? If we didn't have an hybrid model and we were coming with like other ways of doing the higher order corrections, we will need our input to have 5 parameters, and that will mean we will need to run much more n-body simulations. Yeah.
And so, sorry, this is very probably theoretical, but what is the difference between this reg-PT with respect to EFT corrections?
Oh,
you don't know?
I have no clue.
That's not reg. No, big reg PT and.
So I guess the reg comes from regularize.
Yeah.
But regularization is also done in effective field theory. I mean, all the counting term is actually regularizing all the non-linearities.
Yes, I don't know the details.
So yeah, I mean, I'm probably it's just. Does anyone?
Does EFT? Is that the
Yeah. Okay.
Does EFT has publicly available codes that you can download and run in 1 minute?
So I think that there is this PyBird code, which is based, but I think they go only to one loop theory, one loop corrections. Do you know, Chris?
I don't.
Right,
I
so
saw
maybe
this-
that's the, maybe it's just that RECPT is already online and usable by anyone or something.
And so this was by Youngsland?
Yes.
Theory?
No, RECPT is not by Jones, the
It's
theory model is by Jones, yeah, it's Taruya.
Yeah.
Oh, the hybrid one.
Yeah, but they were working together.
Yeah,
But
I would guess, yeah.
One quick question, the last one maybe. So are there any pretty plots from the GP results in the end? It's quite fun to see, like you did an interpolation on these parameter space, right? So for
Right.
each point you have this PK. So like the end result, I want to see how smooth it is overall. Like say you have this interpolated results for PK on this large parameter space. If you were to slice and see of them.
So I don't have a lot of pretty plots yet because I'm waiting for the embody simulations.
Right.
These are just for second order perturbation theory predictions.
Right.
And so the blue line is our final prediction and the black line is the second order perturbation theory.
Right.
Yeah.
Do people on Zoom have any questions? If so, please raise your hand. If there's not, shall we close the recording now?